Hello and welcome back. In this video we'll go over the solution how we could implement a random walk in 2 dimensions. Remember that a random walk is a sequence of events where we decide randomly which direction we move. In a simple one-dimensional random walk, for example, we would decide if we go left or right, or if you would toss a coin and say it's head or tail, for example. In 2-dimensional we would, so to speak, toss 2 coins, one for left and right and one for up and down. So we have 2 random numbers that we need to use. In the simplest case, we would always take steps of the same length, but we could also vary our step size and take short, medium, or long steps, for example. So in this exercise, we wanted to write a program that contains a function to create data from a 2D random walk if we take, for example, 5,000 steps. And we let each random walk start at the origin 0, 0, so the first pair of values is always x equals 0, so y equals 0. And we made the step size an optional parameter, and then the step size is fixed for the complete random walk, so we don't vary it throughout the walk. We could also then plot multiple random walks on top of each other and calculate the distance between start and end of each random walk. And for 200 random walks, we create a histogram or a count plot of the distribution of the distances. Because it's a random walk, we don't expect that this has always the same distance between the starting and the stopping point, but it should be a distribution. So we should also think about how we make our code fast and efficient. We import our standard boilerplate and we start with the manual implementation for solution 1. Here we calculate all our loops ourselves, as well as we calculate the distance between the start and the stopping point. So let's look at the solution. We define a function random walk with a default argument of 5,000 for the steps and a step size as an optional argument which have a default value of. So we always start at x and y equals 0. So we initialize this as a list with 0 as an element. And now we do the random walk. We do a for loop for I over the range 0 to steps. Then we choose the direction. We can use the random number generator in NumPy for this, np random choice, and we choose between -1 and 1. So np random choice will always give either -1 or 1 and do this random. Now we need to calculate the new position. So we, for example, have 1 and 1 in x and y direction, or -1 and 1, or whatever we have. So we calculate the new x position, which is the last element in the previous list. -1 is the index to access the last element, and then add to the step size times the direction we want to travel. And then we append this new position to our array. And we do this until we have reached 5,000 steps, or however many we wanted to do, and this is indicated by the indent. Finally, we calculate the distance between the origin, that is index 0, and the final point by index -1. And we return the points for plotting and the distance. Because this is an array from NumPy, we return the 0 element. Now we execute this function, x points, y points, and the distance, and then do a scatter plot. The size mark gives us the size marker, and we just do a scatter plot of the x and the y positions. And if we do this, for example, we get this nice plot. We start at 0, 0, and then we wander off across the lane. We can also color code as we move on. So we use the walk as a range, between 0 and the number of points, and then the color is defined of how far we are along. So the lightest points are at the start, and the darkest point are towards the end. So we start again at 0, 0 for the specific random walk, and then move across until we end up here. Now we wanted to do 200 random walks and plot the distribution of the distances. Here we're not interested in all the other return values, and one way to signify this is to use an underscore or a dash or something like this, so we don't assign new variables. So we use underscore, comma, so these are the x and y points. We don't care about those, we only care about the distance, and have a list of distances initialized as an empty list and append the distance here. And after we've done this 200 times, we get a distribution. So you can see that on average, we get maybe, 80 or so with a large tail towards long distances, and it's not quite Gaussian in this area. So the solution works fairly well, but is quite slow, as we will see in a minute. And this is because we need to do all the loops ourselves. So let's see if we can make this a bit more efficient. We look at the documentation for NP choice, and there we can see that we can generate the numbers in bulk without doing the loop. We can also multiply the whole array in one step for the step size, and here we use that we always have the same step size. And then we can use the cumulative sum to calculate the path. So let's do this. So we start again at the origin. Then we generate the steps in bulk. So we have here -1 and 1 as before. Now we use bulk to create the 5,000s in one go and multiply this with the step size. And then we add this all together with the cumulative sum. We access the start point and the end point directly, because instead of calculating the Euclidean distance ourselves, we again use on the NumPy library and use the norm for this. And then we can execute this and get a similar result. Another way is, instead of calculating x and y separately, we can handle both of them at the same time using two-dimensional arrays. Now this is another optimization, because here previously we've had two calls to NP random choice, and we now want to get rid of one of them. So now we need to initialize our starting point as a two-dimensional array. We make this as a variable for x and y, so we could easily, for example, extend this to an n-dimensional random walk and initialize this with an NP0 as an empty array, empty in the sense that it's filled with zeros. Now, when we create the steps, and here we have again -1 and 1, and now we need to specify the size in this shape, where we have the number of steps and the number of dimensions times step size as before. And then we follow the same approach as before. Now the new points are concatenated with the cumulative sum. And the endpoint is again the -1 element of the index -1, and we use the norm in order to avoid calculating Euclidean distance ourselves. And we get the same solution. At least visually it looks the same and behaves the same. And we can also do the 200 iterations over the distance, and we see that this time the distribution is slightly different. As we said, it's a random walk, so we expect to fluctuate. Now what we can do is compare our solutions with a magic function called percentage time, and this tells the Jupyter interpreter to measure the timing and tell us how long it took. So remember, this random walk was our manual solution where we did everything ourselves. And as we can see, it takes a long time, 11 seconds, for these 200 rounds. Using the NumPy solution in between, where we have 2 times the call to the random number generator, is already considerably faster with 26 milliseconds. And we can just about cut this in half, as we would expect, by replacing this with a single call to the random number generator. So we can see that the way we implement can have huge impact on how efficient our code